everyone. So a very warm welcome to you all to the Diamond Jubilee Lecture Series organized by the Faculty of Engineering, University of Peradeniya. So we are honored to present the fifth lecture of our lecture series, where we will be discussing about the challenges and solutions related to operating a renewable-rich power system. So as we celebrate the 75 years of excellence of University of Peradeniya, we are delighted to have with us today Professor Janaka Ekanayake, Senior Professor and Chair of Electrical and Electronic Engineering and the Director of the Multidisciplinary AI Research Center at the University of Peradeniya as our guest speaker. So Professor Ekanayake is an internationally respected expert in power systems and renewable energy integration. So today's topic couldn't be more timely or relevant as the world transitions towards a cleaner energy future. So without further ado, I humbly invite Professor Janaka Ekanayake to introduce our guest speaker, and I warmly welcome all of you for today's lecture. Thank you so much.
Good evening, everyone. And thank you for coming, some from faraway places, and we can see large number connecting online. First of all, let me thank Professor Janaka Ekanayake for accepting this invitation to conduct this lecture. The Diamond Jubilee Lecture Series number 5. The Faculty of Engineering, as you may know, is commemorating its 75th year of existence, the pinnacle of engineering education in the country. And under that, we have been conducting series of lectures. The idea is we have a wealth of knowledge in the faculty, and we thought of sharing that with the community, especially our own community, that is the engineering community. That's why we thought of coming on board with the Institute of Engineers Sri Lanka, the apex body for engineering, and delivering this lecture series. Now coming to the speaker, he being one of the first teachers in electrical engineering, and also has been serving for me as a mentor for a long time. Let me, he's not new to the Sri Lankan context. When you say Professor Janaka Ekanayake is there, we expect something elegant from him. So it is my honor to introduce a highly respected scholar and a visionary in the field of electrical engineering and renewable energy. Professor Ekanayake is a Senior Professor and Chair Professor of Electrical and Electronic Engineering at the University of Peradeniya. He is the Director of University Research Council, Visiting Professor, Cardiff University, United Kingdom, Honorary Professor at the University of Wollongong, Australia, and Visiting Professor at the UNITEN, Malaysia. His academic journey began with a first-class honors degree in engineering from the University of Peradeniya, followed by a PhD from the University of Manchester Institute of Science and Technology, or UMIS in short, United Kingdom. His contributions to the field of renewable energy integration and smart grid technologies have been groundbreaking, earning him international recognition. By the way, he is among the top 2% scientists in the world. With over 80 refereed journals and 100 conference papers, he has co-authored nearly 10 books. And Professor Ekanayake's research has significantly shaped the global discourse of sustainable energy. His experience has been sought after in UK, Bangladesh, Vietnam, and Sri Lanka, where he has played a pivotal role in advancing renewable energy solutions. He has a Google Scholar H index of 45 with over 11,800 citations. Stands as a testament to his profound impact in engineering research. Professor Ekanayake is a fellow of IEEE USA, IET UK, and IESL, and has served as an IEEE a Power Engineering Society distinguished lecturer delivering keynote speeches at prestigious conferences worldwide. His leadership extends beyond academia, and he has chaired expert committees on renewable energy and contributed to editorial boards of leading journals in the world. Today, we have the privilege of hearing from Professor Ekanayake as he shares his insights on operating renewable-rich power systems, a topic of immense relevance in our pursuit of sustainable energy future. His expertise and vision will undoubtedly inspire and enlighten us. Over to you, Professor Ekanayake. Thank you very much.
Good afternoon, everybody, and thank you, Lanka, for that introduction. Assuming that the online participants can hear me well. So the topic which I'm going to talk about is operating a renewable power system, challenges and solutions. I'm not a person who would like to sit in front of a podium and doing a presentation, but I'll try. Confined to a place. What I thought was, something is happening. Yeah. Some system. Can somebody from online participant confirm whether you can hear me?
Not very clearly, it's only very faintly. It's very faint. Yeah.
Speaker microphone. Just speaking with. No, sir. Hello? Hello? Hello?
Now it's
Now
better.
it's Janaka.
Let's hear.
Now it is okay, Prof. Janaka.
It's okay. It's okay.
Now good. Okay. Thank you. So I will. Yeah, now it says now okay. Hopefully we have not done any changes. Okay. Yeah. So what I thought was I will go kind of a reverse direction. I will assume that we have an ideal case and start with a blank paper kind of a design, and then look at some lessons that we can learn from other countries, and then finally talk about how we can run a renewable-rich grid and what we need to consider. So I'm assuming, we are trying to design a power system for another planet, which is, there is no political interferences, no technical difficulties. So we are going to develop this power system over there. Any place closer to the earth will have lots of political interference. So I want to go away from. The couple of assumptions that I'm going to make is no conventional generation technology is available over there. Only generation is wind, solar, anything to do with the direct sunlight, and they are all connected through the converters to the grid. So there's nothing called inertia on the system. That word is not there because there are no rotating parts. So it's all has to be redo our mindset and go and design the power system over there. Obviously, the generators that we are going to develop there will be the same. As you can see today, we have wind generators of size of 15 megawatt compared to the size of the largest aircraft in the world, huge. So we can take, develop that kind of large wind turbines. Okay, it's, I don't know what's going on. It's my, Anushka Manohar then. Oh, it says okay. Press okay. The can. I don't know what's going on. So this.
Exit will.
Okay, I'll use my finger, which is more reliable than the. Okay, so basically, right, that has to be minimized, right? Right, okay, you need to. Now it's just a matter of selecting the.
See this. Okay. Submit a link. Yeah, that's my screen. Click on it. Yeah.
Okay. Now you need to put it into the. Okay. Host will Leland make it host. Can somebody confirm whether you can see the screen, please? Those who are.
Yeah, we can see your screen.
Okay, it says okay
Yeah,
for us.
everything
Yes, we
is
can.
okay
So
now.
it's probably a local problem. So basically, these are the turbines, and most of the turbines today are permanent magnet synchronized machines. But when I press enter, it goes to the. Yeah. So, and also this new design which has come out, which is having 2 rotors on single shaft, that also now available for offshore applications. So there are various types of wind turbines which are available for us to generate electricity. Same with solar. Obviously, here we are using crystalline silicon, poly and monosilicon dominantly, but there are other technologies which are available. One of them is this multi-junction solar cells, which basically have a prism on the top, and the prism breaks the sunlight into various components, and the very first component goes and hit the gallium indium phosphate layer, which takes the very first part of the spectrum, solar spectrum. Then the second layer is a gallium arsenide layer that goes to the second part of the spectrum, and the third layer is germanium, which goes to the third part. And now the laboratory efficiencies of these devices has reached around 50%. So they are the kind of latest technologies available. So there are very different technologies, but the grid connection is obviously through a power electronic converter. All the new wind turbines, none of them are coming without the 2 converters, back-to-back converters like this. The whole idea is when you increase the size of the wind turbine, if you go with the old technology, your gearbox size, the weight of the gearbox is usually the same as the weight of the generator. So if you wanted to get rid of the gearbox, you must operate your wind turbine at a very low speed. But if you are operating your wind turbine at a low speed, you cannot connect to 50 Hz. If you are connecting to 50 Hz, if you could remember our basic machines, you have to either run it at 1500 RPM or for 3000 RPM. But the wind is basically, turbine is rotating as 100 RPM. So in order to match that, you are using multi-pole permanent magnet machines which are operating at low synchronized speed. Then you convert it to DC and invert back to 50 Hz. That is, because of that, you definitely need the back-to-back converters. And our solar is, anyway, we all know that it's a DC source. So in order to connect it to our grid, we will need a DC to AC inverter, and also DC to DC converter in some cases to get the maximum power point tracking. So we don't have any synchronized machines. Everything will be asynchronized if you are going to go with solar and wind. So what kind of network configuration we are looking at? Again, as I said, this is a blank paper design, so we don't have a mesh grid or anything. So it's better to go with mini grids because easy to controllable. You can have the full visibility of your mini grid, and you can then connect through various things. And there are lots of research going on for connecting them using the soft meshing devices, basically again electronics. So you have your own generation in the mini grid. You are controlling the mini grid with its own load. That way, we don't need the control center to overlook the entire grid and so on. So they are flexible. They can be operated in grid connected or off-grid mode, and energy trading is possible, and more importantly, demand side measures can be easily introduced. And also, you are not transmitting power for long distances, so the losses will be low. Obviously, any mini grid will require a good smart metering infrastructure to get the visibility. So when every smart meter will send messages to a data concentrator, and there are super data concentrators that will send messages to the local control center, distribution control center, which decide various things and send messages, for example, to change the mode of your vehicle from G to V to V to G. Anything has to be done through the smart meter interfaces. Or you people can come home, plug in their electric car to the plug socket, which is dead. Only the smart meter decide what is the best time to turn on that, depending on the renewable conditions or depending on the price or whatever it is. So there are all kind of the controllability and visibility will be available if you have a good smart metering network. Obviously, if we are looking at a mini grid which can operate in off-grid and on-grid mode, you will need the black start capability. For that, of course, there are now grid-forming inverters. Only difference is that the grid-forming inverter will have a virtual impedance if you wanted to connect them in parallel with other devices, other generators. You will need a voltage regulator to control reactive power voltage. And also you will need an inertia model and a frequency governor. So it's synthetic inertia, synthetic governor, synthetic AVR and so on. And these are some simulations showing what is the response of the virtual machine compared to a synchronized machine. So you can, it's all driven by controllers. So you can tune your controllers where you want to get the best response. You will also require this so-called grid balancing technologies. Now that's the big word here. So I thought we will discuss a little bit. Now remember, we are talking about renewables, no conventional machines in this hypothetical place. So you can't store the resource. The resource will be determined by the weather conditions. So we have to have storage. But if you are going along with storage only, it will be a very expensive affair. So we need to have DSM measures as well to supplement and minimize the storage. This rig and plot shows storage available to us. There are all kinds of storage devices available, mainly lithium ion dominating, but there are supercapacitors, there are sodium sulfur batteries. I'll show you one example, and I'm sure there are lead acid applications still, and as you can see here, the pump hydro also there, but their power density will be low, whereas the energy density and the power density and the energy density will be low in these kind of big plants. We can have distributed energy storage. Any vehicle today, I'm just listing the electric vehicles coming up with the V2G technology. All the technology vehicles are there with V2G. I don't know whether the electric vehicle coming into this country will have this activated, but they are there. So you can buy a BYD today and basically use it whenever you go for camping. You can use it for your own power as your own power source. So that is available. And the other thing is, of course, conventionally what we were doing was we have a resource. We burn that resource. It could be diesel, it could be coal, it could be anything. We burn that resource whenever we required. So there is a demand forecasting mechanism. We know that tomorrow from 8 to 9 this will be the demand. So we planned our generators to burn or use the hydro to get that amount of generation. But today's in this kind of a scenario, there is no resource stored. So you need the best method many countries are talking about is the load following the generator, not generator following the load, because then of course you need a very good DSM measures. So let me very quickly, this is DSM the DSM supplier in California, basically, I can't hear so basically what they do is whenever there is a grid requirement, they send messages to companies who automatically disconnect the certain part of the companies and making them to switch off certain loads, so increase the thermostat ratings of the the ACs and so on. So there are lots of DSM measures happening in the world now. We also have few, but I don't think we are actively using them. And also we will need something to control the voltage. What you are seeing here is a voltage profile in a feeder in Germany. Early morning the voltage was around 1.02 and the power is coming from the grid around 1500 kilowatt to the households. But somewhere around 9 a.m., 9:30, the voltage has increased and the power has become zero. That means the local generation is enough to supply the demand. And after around 9:30, there are lots of solar generation, so the reverse power start flowing and the voltage is going to go up. And here you can see that somewhere around 12 noon, the voltage has almost reached 1.09. This is in Germany. So you need definitely, if you are going to operate mini grids, you will need some good voltage control methods. So, but it is there on our inverters. Remember, our inverters are operating at their full capacity only very little time of the day. The remaining time, there's plenty of capacity remaining. So why not use it as a STATCOM? Static power compensator, where you can, in the daytime, you can absorb reactive power to bring the voltages down. In the night, of course, they have the full capacity to supply reactive power to the grid to boost the voltages. This is something which is required in some part of the country. So we don't, this is now mandatory in IEEE 1547 2018 version. How much reactive power your inverter should supply is specified there. Unfortunately, we don't follow this, and none of the inverters coming into our country doesn't use this facility. So if you use the reactive power, the so-called voltage problems, local voltage problems we are talking about will not be there. But of course, it has to have some way of coordinated operation. For example, if you have in a large ground-mounted solar plant, you definitely need a site controller to send what kind of reactive power requirement is need to be coming from each inverter. So depending on how much capacity available in the inverter, and also depending on the requirement specified in the IEEE 1547. More importantly, if you are going alone with a large distributed, like mini grid, you need a more coordinated control, because you cannot just control one inverter. You need to control these inverters. That's why we have the smart, I was telling that you need the smart meter to achieve that controllability. Once you have that controllability, you can tell each inverter what should be their set point. So these are now kind of small computer programs that you can run on a small control center and decide how to control these inverters. So as I showed you, if we go with so-called blank sheet design, we can get a good system in operation without any rotational machines, without any issues. But unfortunately, we don't have something like that. Already we have a mesh network. This network is meshed in terms of technology, meshed in terms of politics, meshed in terms of anything you name. So it's not that easy to control, like, all these techniques that I'm talking about cannot be directly applied, you need to now think of what is the best way to go forward. But, you start with this. I was showing you the best way to operate a system, but, the system has already evolved. Now, for example, in the UK, they are daily cycling coal power plants. So these are the outputs of coal power plants, and you can see that on 21st April 2017, they have to not to take any coal generation for 24 hours. Because, when you have renewables and when you want to have a commitment to go for carbon neutrality, obviously you need to give the priority to your renewables. So you will end up with that. And of course, whether our machines can do daily cycling, whether you can keep them switch off for 24 hours, all that is not that easy. But this is not something that I produced. This is from National Grid. They are plot. Okay, so I'm just showing, because this was a very big hahoo in UK on somewhere in 2017. Everybody was showing this plot and telling that, see, the wind and solar has taken over the grid operation now in this particular day. Let's look at how others are doing before come up with some solutions. I thought that I will try to compare our operations with South Australia, because there are some resemblance in terms of size, in terms of the transmission line. Having said that, there is a good connection to Victoria, which is, we don't have a connection to any other country. So that is the only difference between us and South Australia. But in terms of the generation, this was the fear that triggered us. February 2nd, 2025, CEB was worrying about this shape, and February 9th, we had the blackout. So the day on Sunday, daytime, you have the minimum demand. Look at South Africa. The demand is the black curve, South Australia, and the minimum demand was 100 megawatt. But you can also see a difference there. There is a negative part, which is not there on our graph. That is because they have little bit of storage. So you can have some flexibility, but I will show you the storage is not big. I was taking everything from the South Australian Electricity Report on November 2023. All my slides are based on, these comparisons are based on that. So in South Australia, this curve, we call it camel curve or the duck curve or whatever the curve is, going down, 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 down. And this was the lowest reported on 16/10/2022, but they were operating without any issues. And you can just look at the generation. We have coal, they will have basically gas, they don't have coal. We have hydro, they don't have any hydro. But the rooftop solar is, you can see that, more than twofold. The ground mounted solar is more than threefold, and the wind is around 10 times more. So the system is operating with lots and lots of renewables, and the battery energy storage is only 5.2% of the total. So not huge amount of energy storage they are using. And this is a comparison of how the rooftop solar took over in South Australia and in Sri Lanka. You can clearly see in 2023 somewhere, the steepness of the curve has gone up because due to the plus scheme that was operated, that was introduced in Sri Lanka, which I'm sure mainly grabbed by the former CEO or the present or former CEB engineers. Lots of houses of CEB engineers has plus scheme in its operation. This is a question we always need to ask. Whether the incentives are coming at the right time. the introducing solar, the whole idea of providing the feed-in tariffs or, whatever the incentives is to promote the market. But when the market comes to certain stability, any country usually reduce the incentives. That is true if you look at any country. Whereas ours so slightly different, and that's why I said designing a system is, you cannot 100% blame the engineers or technologists for this, because that is being also driven by other ways which was introduced to the system. In terms of blackouts, of course, everybody knows about this 9th February blackout. We were telling that there was a grid failure on a part of the network, and that grid failure has created a huge voltage dip, and that voltage dip has taken off around 300 megawatt of rooftop solar out of the system, which has created the immediate deficit of demand supply balance. And that eventually went into a blackout. It's not only here, in South Africa also there was a very famous 2016 blackout. That is very different to our blackout. This was due to several lightning strikes on their network consecutively. This was on a day where they had lots of lightning strikes. The very first lightning struck and taken over part of the transmission network, maybe one line, and that has created the wind turbines. There are 4 types of wind turbines shown in yellow, red, green and blue. These wind turbines were supposed to ride through the fault during the fault, and you can see that some ride through the fault but some couldn't. Then there was a second lightning strike, and that again you can see few managed to ride through the fault without any issue. I don't have a pointer in this one. I don't know what I did. Okay, so there's no point here. Maybe here. Yeah, there's one. Yeah, there's one. So this is the second one. I don't know whether you can see. No, you can't see. That is the second one. And that is again right through by that, and this. Sorry, this is the total, but not the red ones. But then, this was unusual, there was a third lightning strike to a power line, and with that, all the wind turbines, the all 4 could not ride through. And system collapsed. Now, you may see that it's, where the 3 consecutive lightning strikes onto the transmission network is very unusual, but it's not that was the reason. Any engineers are, anywhere in the world are the same. The wind turbines came with the default setting of 2 ride-throughs, and nobody checked that. So it was only set to operate for 2. Now if you look at the South Australian grid codes, it says 8 consecutive ride-throughs. So that is just a setting they had to do in their controllers, but they never knew that it came with 2. So that it triggered whatever the new settings on our grid, on their grid code. Of course, our grid codes doesn't have any of these. So that is a very, of course, one can call it a negligence, but it's partly they are not know about these settings which came with the wind turbines. I don't know whether we know our ones, we don't have a clue. Right. So what measures we took? The CB makes a special request from rooftop solar owners to turn off their the rooftop and other the solar plants from 13 to 21st April this year, because of the fear of having that difficult duck curves, which they can, because especially industries were not there, so they were afraid that they couldn't balance the system. It's not only here. South Australia, you can see that the emergency measures to stabilize the grid. What is it? This include temporary disconnection of some panels. So it's not only here, everybody is trying to use the similar technique to stabilize the grid. Of course, this may not happen every day, but now, of course, we are kind of assuming that that's the way forward. So we need to think of what is the long-term strategy we are having. And they also have batteries. They are having a Tesla battery of 129 megawatt hour battery, which can follow the frequency precisely. So whenever the frequency goes down, the battery will supply energy to the grid. Whenever the frequency goes up, battery will absorb the energy. So they do have very good battery storage, if you could remember, around 5.2% of their requirement. And more importantly, they are the first utility to introduce what we call the virtual power plant. Remember, I was talking about the visibility. Now, if you try to provide the visibility to every single house, that's going to be maybe expensive. So what they did was, they connected several houses together, which include 90 Tesla batteries, each of 6.4 kilowatt hours, 10 Samsung batteries, each of 7.2 kilowatt hours, solar, 4 kilowatt average, and local repository controllers. There's a controller here, which is basically controls the, talking to the other operator. So it's like even though it's individually 4 kilowatt, collectively 40, like 10 megawatt or whatever. I don't know, I can't remember the full capacity. So that way you can see that this is a real plot I reproduced from their diagram. Here the frequency is coming down, and the frequency is coming down, and each site, this is each house, start following the frequency, and collectively they are producing, so my numbers was correct, around 2 megawatt is supplied to the grid. So that's the concept they have introduced to, on top of the centralized storage, they are now using the decentralized storage, which is there in their homes. And this is an interesting plot. Look at these blue ones. This is in 2020, 2021 and 2022. The price of electricity was below $0 per megawatt hour. That means if you operate a power plant, you must pay back to the grid. So it's increasing. That that amount was gone up in 2022. So they were remember the AMO is using 30-minute market with 5-minute balancing. So they were using the market, not the telephone calls, to stop the people coming into the grid whenever they wanted to, to get that balance. So without having a shorter dispatch or shorter market periods, you cannot run a renewable-rich power system. It's a fundamental thing. You cannot do one day ahead planning for renewable-rich power system. You cannot even do 4 hours ahead. 1 hour ahead is okay. This is what everybody is doing now. So we need to go into that kind of a granularity to operate our power system. And this is another example from Japan. Kitsuri is here, so I don't want to pronounce the name of the power plant. Something sounds like Ricasho, but we'll let somebody to get the right name. It has 51 megawatt wind farm with 34 megawatt of sodium sulfur battery, which is 2/3 of the power plant capacity. When you have that kind of the battery energy storage, anything you can do. You can see that here the yellow one is the wind power output, and these are the dispatch order given by the utility. This was a test they run on the power plant, and you can, and the the purple ones are the battery output. So you can see that when the generation is above the dispatch order, battery is charging. Whenever it is below the dispatch order, batteries are discharging. So you can, like these crosses confirm that actual power. So you can see that you can follow exactly the dispatch order if you have that amount of energy stored. Now, who is going to pay for that energy storage? Is it the utility or the supplier, or generator owner? Now, in the UK, it is the generator owner's duty to make sure that not only, I mean, they don't ask us, what you call the energy storage, but there are so many services. I'll show you some services. All has to be borne by the generator owner. Nothing, only few are borne by the grid. This is another plot from Japan. You can see that on this particular day, the hydro was operating fairly at constant value. Thermal was minimum from 4.8 gigawatt to 2 gigawatt. There were a lot of PV, 5.5 gigawatt of PV. Most of them were absorbed by the pump storage hydros and batteries, but still they have to curtail around 1 gigawatt to maintain the balance. So, so you can clearly see that some storage element has to come into the picture if you wanted to operate a grid with large amount of renewables. Just to give you a little bit about the transmission, this is the connection between Petersburg and San Francisco. What you are seeing there, sorry. What you are seeing here is the congestion on in the network before, and the Siemens put up a HVDC connection between the two cities through the Great Lakes. So it was underground HVDC connection, and this is the congestions on their network after that. So the basic idea is to connect the HVDC line parallel to the AC load. Remember, we learned that AC can be controlled using this equation, but now you can add a HVDC also in parallel. In UK also, they are doing exactly the same. They are connecting the Scotland and England using a offshore HVDC line. So that is what they are also planning. And also there are lots of new devices coming for distribution automation. This is SNC devices. They are being deployed in Scotland. The basic idea is you have the sectionalizers, pole mounted, they have current measurements, voltage measurements, and they can operate automatically. So they do give a controller here. This is the control box, again pole mounted. So using that, you can do agent-based control of your network. If there's a fault on one part of the network, you can talk to everybody and make sure that your network, the most part of your network is still live. Only you disconnect a very small part which is faulty. Right. Okay. Now coming to the main topic, renewable-rich grid. Just forget about those diagrams, just to remind you that the past I am putting these diagrams. Now one obvious answer everybody is talking about is a smart grid. We have a network layer already. We can introduce power electronics for power transfer, reactive power control, angle control, for various things you can introduce, and soft normally open points, and then you introduce renewable energy and storage, and you introduce lots of the sensors, the smart meters, various voltage and current transducers, phasor measurement units. Then of course you connect everything using your ICT layer, and you will have the distribution automation, and finally modern control center. I think we have the last one. We have the first one. In between, we have to certain extent in certain places, but not a fully integrated system. So the smart grid will enable the real-time visualization of the power system, support enhancement of power system security, relieve system bottlenecks. I will show you a graph before. Enable self-healing and enable connectivity to consumers. Again, there are people are looking at integrated system connecting all vectors together. Here you can see that district heating, electricity, fiber, water and gas are connected to single network. They are controlled as a single network. So this is the King's Cross initiative in London. They are trying to develop this multi-vector energy system which enable them to kind of, if you can't balance on one vector, you use the other vectors to support you. This is the whole idea. And definitely you will need a good ICT infrastructure. So you can start from home area networks, going all the way to wide area networks, connecting your different parts of your network. And these are some extracts I took from the UK grid code. They call these asynchronous power plants as power park modules. If you look at the UK grid codes, they define them as power park module. Now they should provide firm capacity for a period defined by the grid operator. It's not for entire day or not for a couple of hours, maybe 30 minutes or 1 hour maximum. So whatever the grid required during that 30 minutes, they should provide. And it is automatically comes with the market. They are bidding in the market for 30 minutes. And with that bid, they also make sure that that amount they are bidding will be supplied to the grid. If they can't supply, of course, they have to go to black market and get the electricity and sell it to the grid. So that is what is happening. But it's now very rare because now the operators they have very good prediction tools. Remember, it's unlike those days. You have very good prediction tools, so you exactly know next 30 minutes. Now in UK, you have 30 minutes window to bid. And the gate closer 30 minutes before the real time. And then the real time, between 30 minutes before the real time to real time, you sign all the contracts. Yeah, these are all automatic, there is no people involved, it's all computer. And then when the real time comes, if you have promised that I will give 100 megawatt, that's committed. You cannot say that I don't have 100 megawatt, I'm only going to give you 50 megawatt. If you don't fulfill your requirement, then they are being charged under the spot prices at very high prices. So it's all regulated in that manner. And power park modules, which is the solar, wind and so on, should provide the accurate prediction schedule, which is of course happening in Sri Lanka also, as per the grid operator's time period. This is the critical thing. Whether we have that every 30 minutes or 1 hour time periods where for each hour, 1 hour before that real time asking this prediction, I'm not sure. And in prediction, uncertainties can be met by small energy storage. You don't need huge energy storage to, now you are telling that I am firm up to 95% for this time period. The remaining 5% I get it from energy storage. So the capex for the market operations or the control operation is met by the grid operator. But capex for the providing the accurate predictions and sending them on time, everything has to be borne by the power plant module, power park module. And maintain the security, availability and reliability of supply. Grid code, definitely our grid code doesn't have everything that is required. If you look at the UK grid code, very comprehensive grid code. And now maybe, I can't remember the last time I was reading, it was version 34, issue 12 or something. Every couple of months they issue a new grid code. we probably had a grid code. I don't know when that was issued, and it's like the distribution code was issued in 2019. I mean, I don't know, 25 years ago, and that's the, we have small amendments or the addendums for these grid codes, but that's not the way you have. I mean, every time they have an issue, they change the grid code. And there are mandatory services that should be provided by these renewable plants or the power park modules: the voltage frequency control, reactive power, active power, and float right-through. The grid operator will not pay anything for these. These are mandatory services. So any capex required for this should be borne by the power park modules. For example, in UK, large offshore wind farms use the big resistor buried in the sea, using as a water load. So whenever there's a grid failure, the fault right-through is achieved using that. Because if you don't provide that fault right-through, the penalties are high. The same thing with the reactive power. Everybody has a reactive power compensator. The grid is nothing to do with that. It's a grid code mandatory requirement. But there are other services which grid operator will pay. Black start, fast frequency response. There are so many services. I'm just leaving. So there, if you provide any of these services, you are being paid for that. Okay, not for the mandatory services. The mandatory services are also there in IEEE 1547. Why I am referring to IEEE 1547 frequently, our engineers also, the CEB engineers also referring to that. They don't refer into any other grid codes. They talk about 1547. So, in conclusion, we need to plan with top-down approach as well as a bottom-up. We cannot just assume everything we can do from the top. We need to, like as UK is doing, they change all DNOs to DSOs, distribution system operators, not distribution network operators. So in the UK, every distribution net, the part is, the frequency control, balancing, everything is done by the DSO, not the TSO, not the transmission system operator. So they are being the kind of the planned and operated locally, not centrally. And definitely we must use the decentralized energy storage. If we are having any energy storage, we have lots of hybrid inverters in Sri Lanka. If you look at the South Australian grid codes, or the AMO grid codes, they are talking about how the local energy storage at homes should supply the grid whenever required. So that they are utilizing those energy storage. Whereas we do it without telling CEB because it's not allowed in Sri Lanka, but everybody has a hybrid inverter at home, which is not allowed. Then we have electric vehicles, but none of the vehicles we have right now, I don't think that we have the VTG capability. But I also don't know the new BYDs which are coming into the country, what features they are there. But these has to be, like planned and ask the suppliers to come up with whatever the and the visibility. Without visibility, we can't. I mean, I know that there are a group of CB engineers produce 500 smart meters locally, and they dispatch these 500 smart meters in I don't know where. Then there was another project where the ADB paid to deploy 1,000 smart meters. LECO is deploying their own smart meters by their own initiative, but there's no kind of coordinated action. Those 500 meters, nobody knows where they are going. 1,000 meters, I was part of it, and I was trying to get some data for some analysis, and data is not available, or even if they are available, they are not complete. So nothing is done with these whatever meters we have. And we definitely need to change our dispatch scheduling regime. Right now, I don't know the exact dispatch regime we are using, but we must go with 30 minutes or 60 minutes dispatch schedules. Otherwise, we'll never be able to manage network with rich, renewable. And we must ask the VREs or the variable renewable energy sources to provide this 30 minutes or 60-minute predictions 1 hour before something. Remember, you cannot predict wind 4 hours before accurately. The prediction errors are high. If you do 1 hour before, the prediction errors could be like 2 to 3%, and that can be easily compensated with little energy storage. And we need to definitely revise the grid code. And every plant connected to grid, whether they are synchronized or asynchronized. Remember, if you follow the grid code history of UK, very few, the version 1, version 2, up to version 10, they had 2 types of generators. Synchronized generators and asynchronized generators. So the requirements were different. But when the asynchronized generators became a mainstream, look at the latest version, you don't see that distinction. They consider these asynchronized generators as part of the system. They are supposed to be providing whatever the services the old system was providing. So we need to think of what should be included in our new plants to come. Remember, we are still far away from, 70% by 2030, we still away. But we also have one more hurdle, carbon neutrality by 2050. So we are going, we are supposed to be going towards that target. And if we wanted to go towards that target, we need to plan things at least now. We did things, lots of things we did it without any plan. Whether it's the politicians who should be blamed, or the CEP engineers, or the UCSL, I don't know. But at least now, if we wanted to go to those targets, maybe not 2030 is too early to do a very concrete plan, but have a plan, stick to the plan, and absorb electricity and other services according to that plan. Otherwise, we will always asking solar plants to curtail their supply time to time. We will always debate about whether we should have coal or gas or whatever. I think it's a lack of planning. It's not. I'm not blaming CB. CB come up with a rolling plan, but that plan is usually not implemented due to various reasons. I'm not, like these NDCs, national determinant, whatever. These are not done by the energy ministry. They are done by the environmental ministry. So there is always lack of communication. So with that word, I stop here. I'm happy to answer any question. Those who could remember, that tree is no longer there.
So first of all, let's move forward with physical audiences. If you have any questions, please raise your hands and I can ask any questions. And at the same time, for the audience in the Zoom as well, you can drop any questions you have in the chat.
As you share transactions, you wonder where we are. It is only in that this tragedy, the situation is high, and maybe as always. So, difficult question to use. Yeah, I have bit of a threshold. Because, as you know, the Legacy Act have been amended last year. And now, unfortunately, it's supposed to be amended again. But you are aware of this, those changes that are proposed, not necessarily the high technical sense, but the system, management and responsibility. Are we getting closer to what we are looking? Are we moving away? Any idea on that? That's what I would like to.
I mean, nobody knows how these reforms will take place. Maybe Lilantha knows better than me, is in that committee. It's, as I said, one of the key points should be the introduction of DSOs. Those who can manage the local grids are not operated from the central control, because if you have DSOs in operation with new reforms or whatever, then anything happening, you can stop there. You don't, that won't cascade it to the entire country. But what is now happening is everything is controlled by a god up there, and anything, they don't have the, I mean, if they have the full visibility, yes, but they don't have the visibility either. Yeah. So without visibility, in blind they try to do things. So I think reform should, I don't know, I don't have a clue about the reforms. I was kind of, completely backed away from the CEB or the power sector affairs. But anything which should be done should be that. That should be the key.
Wonderful presentation, Professor Janaka. I want to paint a scenario to you, and then I would like to hear your comments. I like to use the term prosumer. That's rooftop solar and battery storage with smart devices. So produce consumer. And now you incentivize this prosumer because you're going to have time of day metering, market rate tariff. So now at peak demand, the tariff goes up, and then 4 o'clock in the morning, the tariff is low. So the prosumer can play his game, his or her game. The prosumer could be a commercial enterprise, industrial, or a residential. That's number one. Number two, we are going into renewables, wind and solar. Like in India, we should again use the tariff to encourage developers to have hybrid of wind, solar and battery storage, because they're going to tell him, if you give us generate power during peak hours, you're going to get a high tariff, and at 4 o'clock in the morning, low. So, and the scale up potential for these two are tremendous, and that's what's going to help us attain renewable energy dominance. Comments, please.
Yeah, I mean, the customer empowerment is being discussed everywhere. The prosumers are being forefront. If we have prosumers, as I showed you, maybe not prosumers in isolation, prosumers as a virtual power plant, where you have the good manageable group of customers, where you can generate your own, you have peer-to-peer trading if you want, and the grid can manipulate the tariffs the way they want, and they also can supply various services to the grid and earn money. So I think we need to go into our old cooperative society concept with these prosumers, because we were good, we were, as a country, we were having a very good cooperative societies. My father was working in cooperative society for 75 years. So he was, one of the key person. He died in 99. I think we need that. That's why in UK now they are talking about consumer groups. That is becoming, a key. So that's something we should do. But what has happened over the years? We kind of anything happen to any place, we start compartmentalizing our houses, our grids, everything, so that connection is no longer there. So establishing that will be difficult. So only way is to use the price signals to do something. Same thing with renewables, as you very correctly said. If we have the markets, 30 minutes or 60 minutes, what you say will automatically will be taken care of, because the market prices, as you see, you saw in South Australia, market prices have gone down to negative values, because at that time they don't want any electricity. For example, on a day where your demand is 100 megawatt, why you need any generation from anybody? So that then market will automatically drive everybody down. So, but whether we have this large coal power plant, we don't have the flexibility. That inflexibility is something we need to take care of as well, because renewables are inflexible in terms of the resource, and the coal power plant is inflexible in terms of operational strategy. So that inflexibility we need to somehow. So the CB has a challenge definitely. It's unlike my so-called other planet examples. It's not that easy.
2018, 5 researchers from Greenland. They analyzed the failure in South Australia, which was correct. And in the analysis between certain Wimalasurendra technique, they came to the conclusion that what we figured saw was the storm which knocked off quite a lot of regeneration. And then the Hayward interconnection supplying power from Victoria to South Australia sent power, and that constituted a kind of a bottleneck. And with that, the power angle increased and ultimately disconnected. So what the conclusion they came to was that if that disconnection was sensed early, that separation was sensed early, they have averted a complete blackout. What is your view?
I mean, again, I'm very much talking about the visibility. I mean, visibility should be there in every place. Now, if you had phasor measurement units, now they will send you not only the voltage or the current magnitude, they also start giving you the angles. So immediately you start seeing that the angles are opening and you cannot send any more power. You have controllability on the networks, but right now in Sri Lanka we only have two PMUs, one in Kothbale and one in Biyagama. That also nobody uses. I was trying to get the data during that so-called somebody make fire and the stripping thingy. I was trying to get data and trying to analyze it, but data never came. But we need to get the data and analyze. There are ways to analyze. You can, if you have at least those two PMU measurements, I could have analyzed and told where exactly this issue is. I did an analysis based on the previous to that blackout, there was a partial failure 2 weeks ago or something. I managed to get that data and I published in a book. In fact, it was published by Wiley. So I published that analysis with the way to analyze, what is the maths behind that analysis. So you can do that. Visibility is definitely one of the key. Excuse me. There was a person who asked very first.
Yes. You asked, so the question is because it was so this is from Peradeniya. So he's asking, is reaction time a technical limitation? Microgrid operation, for example, detecting frequency or computer changes, sending data to central points, and coordinating the controls faster.
I mean, obviously, one good thing about synchronized generators is there is absolutely no reaction. Inertia comes immediately after it sees a frequency disturbance. I mean, if you are going to go with the artificial inertia, obviously your controller has to get the measurement and do some processing and provide that.
I was the question I want to ask is, when we introduce the communication elements to the grid, we automatically expose our grid to the threat vectors and foreign threats. So how prepared are we to encounter those threats, and what are the mitigation mechanisms there?
I'm not an expert on cyber security, but for the grid operations, we never use corporate networks for certain critical communications. Usually you use your own point-to-point communication or dedicated networks, so you don't let anybody to come into that part of the, I don't know in CB, but I 100% knows at National Grid UK, you cannot use your emails at home. The emails can be only operated when you are in the office. So even their corporate normal network is not exposed, the restricted. I really like that idea, because for Sri Lankans, we don't have time to work. We work 24 hours, right? When you don't have emails at home, where you cannot communicate with, for official things, you are at least looking after your family, and, I think that, I like that idea. But unfortunately, and also National Grid, the other real good thing I like is they have a no office policy. The tables are open. No table is reserved to no engineer. So all you need to do is go early in the morning, grab your table and work. If you are going away for more than 2 hours, there are lockers given to you. You can put your stuff and go. So that way, you kind of minimize if you look at our officers, half of the officers are not utilized, but there's a name on it. So that's a bit of that's our culture, and we don't even let anybody to come and stay in that office during the time you are abroad or something. You think that that's your office, So there are a lot to learn, not in engineering terms, on other terms as well.
Yeah. Number one is how it's amount of important is connectivity. Now we have so many inverters, but none of them are connected to any control center. No smart energy meters. Now going forward, we don't have a proper simply IoT. Sri Lanka is very much lacking to IoT. This power network is going to be smart. Our network should be IoT. So to start with, it can be inverters and smart meters. So now, if we don't have proper standard coming, still even if we spend the batteries whatever, how realistic it will be for the stability. That is even for whatever the data analytics now what we are talking about, data should be available. So to generate data, the connectivity should be there. That is one thing you are comment. And the other thing is, it's this DSO. It's a good concept. But in Sri Lankan reality, do you think areas like now, rural areas, whether the DSO will be a reality because they don't have enough generation? That's my second question.
Okay, let me start with the DSO question. Obviously, DSO is required for certain areas in Western Province and maybe it's in Scandi, that. So the DSO concept, no point of taking to a very rural area where you only have very limited generation as well as very limited load. You don't have any problem of excessive amount of solar in Ampara, I don't know. I'm just guessing at rooftop level. You have maybe you have lots of ground mounted, but they are always connected, so they don't have any issue. So the DSO concept should be carefully planned. I think, we do have kind of a DSO LECO, but LECO doesn't have the DSO kind of thing. LECO is a network operator. Okay? But LECO is, when you look at LECO, they are introducing the visibility onto their net. But they cannot really they just purchase electricity and distribute. Even though they have that visibility, they have good, network with lots of renewables, they don't have the controllability. So I think, that's kind of a model I'm talking about. I'm not talking about the DSOs established in, part of Jaffna or something, maybe it's complete. So we need to first identify what is the, it may not be the word DSO, but strategic, breaking the network in strategic ways and giving them the controllability. I don't know whether the reforms are doing it. I don't want to ask that question from Lilanda, but that's something unbundling was the one which we started a while ago, but whether we want the unbundling, I don't know. Anyway, so definitely, if you have an entity which has the good visibility, as you very correctly said, good smart metering network, with smart meter also talking to the electric vehicle as well as the solar PV. And then controllability or control centers locally. There is a control center, there is a Kandy City control center. But that control center is network operating center, not a system operating center. So I think we need to think of that as a model. Otherwise, whatever we do, we will trying to get this. Just imagine how much data we are going to generate. And can the control center, single control center, analyze these data and do that controls? It's impossible. If smart meters will send data every 15 minutes, average value, active power, reactive power, voltage, current, so many data points. You just ask CB these two areas. CB had Katunayaka 500 meters, LECO had 500 meters in Nigambo. If you can try to get that data and see how they have analyzed and utilized that data to manage and control their network, I don't want to comment on that.
Thank you. My question is, when we design inverters, they imitate the STs, single generator. In 100%, there is a high inertia and damage. In 100% renewable systems, do we need to meet that, or we have different control methods?
There are two types of inverters. One is called the grid following inverter, and other one is called the grid forming inverter. So what you are referring is grid forming inverter. So the network, the distribution system operator should decide where they need the grid forming inverters and where they require the grid following inverters. Now, for example, having grid forming inverters at rooftop systems is just a waste of, because remember the controllability that you are going to introduce to these, other than the voltage control. Voltage control is something required by everybody, but grid forming inverters are required by large solar parks or large wind park. where they also can act as synchronized machines and supply the grid whenever there is a grid failure. The remaining inverters should be grid following inverters. They just wait until the grid to be formed by somebody and then just follow it. So that is the concept we should have.
So, there's no the question was answered. So, this is from me. So, he's asking is what would be the goal of biomass, waste to energy, biogas systems in the future?
I mean, if we are heading towards the decarbonized energy sector by 2050, you cannot just work with solar and wind. You need the good energy mix. So we need to select every possible energy source which is in net terms not producing carbon. Net, because we are talking about net carbon emissions. So in net terms not producing, so there's no restriction as such. I mean, we may not use the certain technologies today, but in 10 years' time, maybe even marine technologies will be mature enough to be used as a mainstream technology. So we are heading towards 2050 decarbonized grid, 25 years away from us. Definitely, most of us will not be there, but of course, the people in the back will be there. But so, in that journey, we need to plan these things, that plan is the one which is lacking. We need to plan our journey towards, we have the committed NDC, that is there, but not the plan or the pathway to reach there. So when you reach there, you need to consider every single power plant, resource, not solar and wind, which of course unfortunately has become dominant right now, but I'm sure Farah has a lot more to say about biomass. They are equally carbon neutral. So, there are a lot more ways to achieve that.
You say, biomass is a open resource, work power resource. For the biomass differently. What to say is smart people, potential is to bring. Whatever reason, government has not followed. I remember they were saying that they want to have become sterile government, all that was it. Also, India is the right path way to incentivize to get the money and put money.
So, coming back to the prosumer business, if we are deciding strategic DSO, so whatever the system operators, strategic system operators, of course you don't need smart meters in diverse areas where you don't have the lots of energy usage or lots of renewable rooftop solar, because consumer, somebody who is paying very little money, why should he or she pay for the smart meter? So the smart meter should bring benefit to the consumer, definitely. So it is definitely the LECO area which is rich of renewables, which has high-end consumers. I'm just assuming not all the LECO areas, certain areas, and also there are certain CB areas like in Dehiwala, there are a few areas. Those areas will definitely benefit from smart metering. Now, the whole idea of the smart metering trial that we started in Negombo, and I saw that Tilak is here on the cyber audience somewhere, Tilak. Dr. Tilak Semblapide. Now, we too kind of decided what kind of tests we should do using this network. We came up with several tests, introducing a temporary tariff for these guys and see how the people are reacting. So all that was done. We had reports on that, but nothing was implemented, unfortunately. So I think it's a good time to deploy smart meters for these strategic areas and utilize some special tariff mechanism and incentives to use them as prosumers to provide not only energy but also services to the grid.
Thank you so much. We're happy with the audience as well. So,
yes, so once again, thank you so much. And we are moving towards the end of the lecture series, the 5th lecture series for the Diamond Jubilee lecture series, where we celebrate the 75 years of excellence of the University of Peradeniya in engineering faculty. So now I would kindly like to invite Dr. Navaratna to proceed with the vote of thanks.
Okay, good evening, ladies and gentlemen. On behalf of the Faculty of Engineering, University of Peradeniya, and the organizing committee of the Diamond Jubilee lecture series, it is my great honor and privilege to deliver the vote of thanks for today's insightful and thought-provoking session. First and foremost, I extend our heartfelt gratitude to Professor Janaka Ekanayake for delivering a truly engaging and enlightening lecture on operating a renewable-rich power system, challenges and solutions. Your deep insights and practical perspective on the future of energy system have broadened the understanding and sparked the meaningful conversation on sustainability and innovation in power system. Thank you very much, sir. I would like to sincerely thank all the eminent professionals, engineers, academics and students who join us today for this event, both physically here at the IESL and also via Zoom. Your presence, attention and engagement greatly enriched the event and reaffirmed the value of knowledge sharing within our engineering community. Our appreciation also goes to the Institution of Engineers Sri Lanka for hosting this session here and also continuously giving this support to the faculty throughout this lecture series. A special thanks to Dean Engineering, Faculty of Engineering, University of Peradeniya for his support organizing this lecture series which is part of our Diamond Jubilee celebration. Also to the organizing committee who are working diligently behind the scene to ensure that we have smooth coordination of today's session. Finally, all participants, thank you for your time, enthusiasm and continuous support